this computer. There we are. So now we start with the registration and we start with the lecture. That is, okay, I already said this is the course, blah, 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 so no problem. Now, let's start with something very simple, but just to make sure that we all remind where we are coming from, let's start with radioactivity. Radioactivity, as you know, comes from Germany was a German discoverer. We go back to November 1895, when Röntgen discovers X-rays. That's pretty much the device where he found this amazing rays, and this is the famous first X-ray of the wife, of the hand of the wife of Mr. Röntgen, that was published on the New York Times, you see, on January 16, 1896. But only 1 year later, Becquerel in France discovered that these strange rays can also come from natural sources. So this was the discovery of the natural radioactivity. Both Röntgen and Becquerel are also they have their name in the units. Unfortunately, the Röntgen as unit is now abandoned by the international system, while the Becquerel is still valid, and is 1 disintegration per second is the unit of the activity. Röntgen is the unit of the charge produced per unit mass. It's been replaced by the Coulomb per kilogram. Now, where is the radioactivity, the natural radioactivity coming from? Well, the story, as the people in nuclear physics know extremely well, comes essentially from the nuclear stability belt. You see that if you take the light elements here, the number of protons, the atomic number here, and the number of neutrons here is essentially the same. But when you move out of when you start to have heavier and heavier elements, the number of neutrons starts to be much higher, because of course you need more neutrons, so more strong force to compensate the electromagnetic force that is repulsive between protons in the nuclei. Now, what are the type of emissions? This you also know very well. I mean, the alpha emission is characteristic of the heavy elements. It's the consequence of tunnel effect, is a quantum mechanics effect. And so you can have a heavy element like americium-241 that decay into neptunium-237 with the emission of an alpha particle, which is nothing else than the helium ion, with 2 protons and 2 neutrons. Then you can have down in the bottom here, you can have gamma emission. In that case, you have an excited nucleus that decay into the ground base with the emission of a photon, of a photon. This is exactly the same mechanism that you have in. But can I ask you a question? Do you see me? No, of course not. You don't see me, right? We
can see you.
Ah, you can see me. Wonderful. So I can go back to this because I don't see myself, you know. So I was wondering if you see me, but this is perfect. And finally, we have the beta emission, and we will see there are 2 types of beta emission. One is shown in this cartoon, where you have a neutron that decays into a proton with the emission of an electron, but you can have also a proton that decays into a neutron, and in that case you must have the emission of a positron. Which we will see in a moment. Now, alpha particles, we have already discussed this decay of the alpha particles. This is the decay now of the beta decay, where you see, for example, you have now potassium 40. Now, potassium 40 decays with the emission of an electron, which is called. This is not an atomic electron, of course. This is important also for radiation protection. This is a nuclear electron, so it comes from a nuclear process, not from an atomic process. In association with the emission of the beta of the electron, you also have another particles which is an antineutrino, which has no charge, but brings part of the momentum in the reaction. And the other decay, as I told you before, in that case you have the emission of a neutrino, and here we have, for example, a decay of a heavy element. You see that here you have the emission in this case goes into a beta plus particle, so into a positron, and the corresponding particle emitted is a neutrino, not an antineutrino. Keep in mind that beta plus are, of course, very unstable because they tend to collide with electrons. There are many, many electrons in matter. So every time you have a positron emitted, very quickly this positron will collide with an electron and will annihilate, emitting two gamma rays. This gamma ray emission is very useful in medical physics because can be detected by PET detectors, and we will have a lecture on PET detectors later in this course. Again, this is the neutron versus charge plot that shows here that isotopes in this region here will emit beta particles to become more stable. You see, so essentially they will lose here. They, in some way, in this position, let's say that you have an isotope in this position here, you have too many neutrons, so you can use beta decay to go into a more stable position, because then neutron is decreased by 1 and the number of protons is increased by 1. In terms of interaction with matter, that for radiation protection is the most important part, you also know very well that gamma rays are very penetrating, beta rays are poorly penetrating, and alpha particles are stopped immediately. They lose all of their energy, even on a paper sheets or on the surface of your skin. They do not really represent any health hazard for external exposure. And the radioactive decay laws is also, I'm sure, very, very well known. So if the decay is characterized by half-life, so the time that you have to wait until 50% of your material has decayed, and this can be expressed by this formula. So it's, of course, it's an exponential decay. So the amount of material, of radioactive material, decays with time, starting from H0 times E2 minus lambda T, where lambda is the decay constant, and this, of course, is given by the logarithm of 2 divided by the T1 half. And of course, instead, if you look at the accumulation of the daughter nuclide, you will have to use this formula. That's also very important when we will touch the nuclear medicine aspects. Radioactive units. As I told you, this is the Röntgen down here. You see it's 2.55 per 10 to minus 4 coulomb per kilogram. This gives you the amount of charge released by radioactivity in air. The Curie is 3.7 per 10 to the 10 becquerel. 1 becquerel, I told you, is 1 disintegration per second. This is a funny unit, but still very much used, actually, the Curie. It's the activity of 1 gram of radium, so it comes, of course, from the discovery of Marie Curie, while the current unit for the exposure is the coulomb per kilogram. For the dose unit is the gray. The dose is defined by the energy absorbed per unit mass, is measured in gray. And the kerma, instead, is slightly different because the kerma gives the kinetic energy of secondary particles divided by the mass. This is different because this is an absorbed dose. This is an energy released. Not necessarily they are the same. Not necessarily they are the same, and this can be easily shown here. This is now the depth dose distribution for X-rays in matter. If you take the kerma, oh, I'm sorry. If you take the kerma, this is a log scale. So if you take the kerma, you see that this is perfectly exponential. Now, this factor here, this phi, we will discuss it later, but essentially it's a perfect exponential loss of dose in matter, which corresponds, if you want, to the Lambert-Beer formula. You know, every time you have light going through matter, the decay is exponential, is always like I0 e to minus mi x, and this is the Lambert-Beer formula. However, if you take the dose, you see a strange effect here. You have the exponential decay starting from a given point, but before this given point, you have a buildup. This is simply due to the fact that at the beginning here, you produce ionization, so you release electrons, but these electrons will deposit their energy outside of the volume. So you see, at the beginning, you start very low, then you reach a maximum, and then you start to go down here when you have equilibrium. So when essentially, when the electrons produced in the previous layer are compensated by the electrons produced in the following layers. This is actually, of course, as you can imagine, very important in radiotherapy. You see that essentially the maximum dose is not the entrance dose, it's not the skin dose, but is a little bit more deep, depending on the energy of X-rays, is a little bit more deep in the skin. You reach the maximum dose and then the dose goes down. So as I said, that's something we have to agree. Oh, I forgot to tell you, but of course, Marietta, Leon, my former students know it already. Anytime you want to ask a question, just stop me. I cannot see your hands raising because I see the full screen of my slide, but just open your microphone and speak. Just tell me I have a question, okay? Do you hear me? Can anybody tell me yes?
Yes, we hear you.
No, thank you. Just because I don't see you, I start to be afraid that I was speaking to myself for 1 hour. That was depressing. So the dose, as I said, is measured in gray. But there is one important thing that you have to understand immediately for those that don't know. Not all the type of radiation has the same biological effects. So to measure, and the dose is a purely physical quantity. So you can have 1 gray of alpha particles, you can have 1 gray of X-rays, you can have 1 gray of beta particles, 1 gray of whatever. So to distinguish between these different radiation, people invented a new quantity called sievert. We will come back to this one, especially in radiation protection. Essentially, the equivalent dose is given by the weighting factor times the dose. And for X-rays, gamma rays, and electrons, this weighting factor is 1. So effectively, 1 gray is 1 sievert. But for example, if you have alpha particles, then the weighting factor is 20. So for example, 1 milligray of alpha particles corresponds to 20 millisievert. So it's much, much more effective. Biologically, is much more effective. We will see the weighting factors when we will study radiation protection, not when we will study radiation therapy, because these weighting factors are really designed for radiation protection purpose, so low doses. If we go to high doses, we have a different concept. We will use the concept of gray equivalent, which is essentially given by the product RBE times the dose, or RBE weighted dose. And this RB is generally lower than the weighting factor. This we will see. I mean, the effectiveness, the relative biological effectiveness depends on the dose. Okay, which kind of doses we are familiar with in our world? We are familiar to a huge range, you see, of doses. We go from, this is in millisievert, it's a log scale. We go to 10 to minus 2 up to some 10 to the 6 here. So it's like 8 orders of magnitude. But you are familiar with these doses because you see this very low doses. For example, here there is the dose living 1 day on Earth. If you live 1 day on Earth, this is the dose that you receive unavoidably due to environmental radiation. If you sleep with another person, you get a higher dose. And that's because you are irradiated by the person that you sleep with. We are actually radioactive because we eat, you see, if you eat 1 banana per day, it's down here, you get quite a substantial annual dose because if you eat 1 banana per day, because bananas contain potassium. One isotope of potassium is potassium 40, and this is radioactive, and so you are radioactive. And then if you sleep with the other person, this person will irradiate you, and then you get a higher dose. So, you know, depending on how long you sleep and how many persons you sleep with. Or, of course, if you fly, which is now impossible with COVID-19, so we have no more lower exposure to radiation thanks to COVID-19. But if you have pneumonia due to COVID-19, you will do a lot of chest radiography, as you see here, which is 0.1, approximately 0.1 milligray, much more than sleeping. You have to sleep with probably some few people to have the same dose as in X-ray. Then you have mammography, which is a higher dose. And then you go to space. For example, on the International Space Station, 1 day in space is about 1 millisievert, which is very close to 1 year on Earth, 1 full year on Earth. Other procedures are even more higher dose, like a full body CT scan would be 10 millisievert, which is close to the maximum annual dose for radiation workers, which is approximately 20 millisievert. That's definitely not the higher dose in radiation protection, though, because, for example, in exceptional cases, in emergency cases, Fukushima liquidators, you are allowed to go up to 100 millisievert. Actually, these people were really, they were working until the dosimetry were indicated 100 millisievert. At that point, they had to leave. But you see, radiation is strange. If you live 1 year on the Guarapari beach in Brazil, that is this wonderful place that you see here, then you will get a dose which is even higher than a Fukushima liquidator. This is due to the monazite sand, which is very rich in thorium, and the radiation will be very high. Of course, nobody really lives on the beach in Brazil, even though maybe some of us would like to, including myself, but that's real. I mean, there are areas on Earth where the dose rate, actually like Guarapari Beach in Brazil, the dose rate is comparable to the dose rate of Mars. You see Mars here. Even though the dose to go to Mars, if you want to go to Mars, it's a long trip. You have to go through deep space, then you have to stay on Mars, then you have to go back. The total dose is in the order of 1 sievert. That starts to be a very significant dose if you think that 4.5 sievert is the average lethal dose for humans. So if you are irradiated acutely with 4.5 sievert, this is lethal for 50% of the humans. So, but we know even higher doses. First of all, you kill a human, but if you want to kill a cockroach or a beetle, you need a much higher dose. There are animals that are much more resistant to radiation. And second, even humans are irradiated with much higher dose in radiotherapy. But the trick here, and the work of the medical physicist is exactly this one, the trick is that you want to give a very high dose to the tumor, having a small dose to the normal tissue. So you want to be able to focalize your dose on the tumor and to spare the toxicity of the normal tissue. This is the work of the medical physicist, and we will spend quite a lot of time discussing how to do it, how can we do it. And finally, if you are a virus or a bacteria, it's even much more difficult to kill you, so that if you want to sterilize the syringe, with radiation, you have to give a much higher dose, which is actually done. I mean, the syringe that you use, I don't know if you use syringe, but you will have probably seen these plastic syringes. These are actually sterilized with radiation. So you see, it's a very broad range. Any questions so far? Curiosity, question, you want to know how much is the dose in your flat? Do you think that the dose in the flats are all the same, or do you think that they are substantially different, for example? If you live in a flat, what can be the difference? I don't see your...
Basement or first floor.
For example, who is speaking?
Leon, that's Leon.
Leon, why is it different, basement or first floor?
Radiation through radon.
Exactly. In that case, I didn't put it here, but you are perfectly right. It plays a large role in this dose of 1 year. More than 50% is due to internal exposure to radon, which is a gas. And this gas, as Leon correctly said, accumulates in the basements. So if you live in a nice Arctic house, you know, on the top with a huge terrace, and you keep all the windows open, you will get a lower dose from radon than if you will live in a basement, you know, in a sad basement, like many poor students are forced to do. And then in addition to seeing very little light and having a low level of vitamin D, you will also get a high level of radon. And what about geographical distribution? Is the dose the same everywhere? We saw Guarapari Beach, but do you think that in Germany there are significant differences if you live in Frankfurt or if you live in Munich? Or you have any idea, or is the same, is always the same? Nobody knows?
So I'm pretty sure there's a difference, and I'm sure you will show the map. On the
I think I don't have the map. I'm sorry. This was for... I don't have the map here. I think I will show it maybe in the radiation protection. There is in Germany, there is a difference of approximately a factor of 2 between different areas of Germany. Partly due to the difference in altitude and partly due to the difference in the minerals, you know, in the force of the, you have more or less radon around, but there is a factor of 2 very easily. And if you are in China, like Jan, the difference is actually a factor of 10. So there are areas in China that are 10 times, that have a 10 times higher background radiation than the normal background radiation at the sea level. Same if you are in Tibet, for example. If you are in Tibet, which is also China, I mean, sorry, it's also part of China, but it's a little bit special. In that case, people live at altitudes as high as 5,000 meters above the sea level. And in that case, there is a lot of cosmic radiation. You really get much more cosmic radiation than at the sea level. And then again, the average dose is some 5 to 6 times higher than the dose at the sea level. Any more questions? So far, I am the only one asking questions. Is there anybody else, or I should go on and ask difficult questions to myself? Okay, let's go on. Nothing to do. So how many ionization in our body? That's something we have to clarify. I mean, is ionization a rare event or is a frequent event? This we can easily calculate, let's say. So we say that the annual dose is about 3 millisievert, but this means approximately 1.5 milligray, because as I said, there is quite a large component from radon. So 3 millisievert is not all gamma rays, but there is a component of radon. This means, according to the definition of Gray, 1.5 millijoule per kilogram, and this means, if you remember the conversion joule to electron volt, 9.4 per 10 to the 15 electron volt per kilogram. Now, The average energy per ionization is about 34 electron volt. This is pretty much a magic number if you want. I mean, it's very variable, but if you take the water molecule and you look at the average energy that you need to ionize an electron from the water molecule, it turns out to be approximately 34 electron volts. So this means, considering the energy per kilogram, we have approximately 2.75 per 10 to the 14 ionization per kilogram per year. Now it depends on the weight, of course. If you are like Marietta, then you get very few ionizations, but if you are like me, you get a lot, because for 70 kilogram, you get about 6 per 10 to the 6 ionizations per second. So it's a large number. We are talking about millions in 1 second. So it's not a rare event, only due to background radiation. So only due to background radiation, you have approximately 6 per 10 to the 6 ionizations per second. Is this a problem? So are we going to die for that? Well, the first thing we have to see is that the biological effects of radiation is not related to the total energy deposited. This is a simple example. The lethal dose for a human, we say that, is about 4 gray. Now, the energy absorbed, again, if I take a 70 kilogram man and not a light person, this is about 4 joule per kilogram times 70 kilograms, so it's 280 joule, which is 67 calories, but 67 calories, you see, if you use the usual way to calculate to relate the calories to the temperature, essentially correspond to 1 sip of a cup of coffee. You see, if you take a difference in temperature between 60 degrees, which is the temperature of the cup of coffee, and 37 degrees, which is our temperature, then you immediately find out that you have, using the heat capacity, 3 ml, a volume of 3 ml of coffee. So the radiation effects, that's important to understand. Radiation effects has nothing to do with the thermal effects. This is very important for 2 reasons. The first one is that you know that the best dosimeter, we will see that the absolute dosimetry, when we will talk about absolute dosimetry, we will see that the best dosimeter is a calorimeter. So the calorimeter is a machine that is supposed to measure the dose based on the change in temperature. This is possible, is wonderful, is absolute measurement, is not relative, you know. But the caveat is that he has to look for very, very, very small temperature changes. The second point is that for other type of radiation, like non-ionizing radiation, you know, electromagnetic radiation, the thermal effects are by far the most important. You know, of course, if you take like the microwave region, as you can imagine, if you are stuck in a microwave oven, you die, but you don't die in the same way that you die for ionizing radiation. You die because of the heating effect. And even at lower frequencies, you know, like in the cell phone, in the let's say in the terahertz and in the kilohertz region that is far away from the microwave region, you still have significant thermal effects that can cause damage. But this is not the case for ionizing radiation. So when you go to very, very small wavelengths, like for ionizing radiation, the heating effect is absolutely inessential. So another important physical characteristic is the LET. The LET is the linear energy transfer. Traditionally, this will be surprising for our colleague from Kernphysik. In radiation protection, we always in the radiation therapy, we always measure the LET as kV per micron, which is strange for physics, because in physics you measure it in MeV per gram divided by square centimeter. But the reason is that, first of all, we assume that the LET is calculated in water, so that the density is 1. And second, for historical reason, we prefer the KeV, kilo electron volt per micron region. Just to give you immediately an example, of course, the LET depends on the velocity and on the mass. And we will see that these kind of numbers, if you have 15,000 keV per micron, this is very high LET, only possible when you have a slow and heavy element. Very low LET, like 0.3 keV per micron, it's only possible for fast and very light charged particles. It is really only defined for charged particles, even though you will find it also associated to X-rays or gamma rays, but in those cases, it really refers to the spectrum of the secondary electrons produced by these photons. Sorry, this is in fact the spectrum you see that I was mentioning before, and of course this one you all know very well. And now let's see a little bit the interaction of photons and matter. Okay, any questions so far? This is just a simple introduction. I don't expect many questions, but if there are, please ask. Also, if you can someone remind me at what time we have to stop? 6:50, right?
Yes, I think 6:50.
6:50. Okay, 6:50. So we still have some time. So we can, I think we can use this lecture, you know, to kind of familiarize with the very basic topics before we go a little bit more in detail from the next lecture. Interaction of photons and matter. This is also a topic that physicists know very well, but generally speaking, you see, this is what happens to the photons. This is vacuum, this is material, these are neutrons, and these are fast ions. Completely different interaction. Here, every point here is an ionization. When you have photons, photons travel quite a lot. Then they can have an interaction. This is typically a Compton. And in some cases, they can be absorbed completely. And if, for example, if there is a photoelectric event. In this case, for the neutrons, they travel very much. When they interact, this is a scattering, there is an elastic scattering of the neutrons, and the dense track that you see here is a recoil proton. In fact, of course, neutrons are not charged, so they cannot induce any ionization themselves because there is no Coulomb interaction, but they can have a strong interaction with the proton, and in the water, they will see a lot of hydrogen, so they can have interaction with the hydrogen in water. And then the recoil, hydrogen is a low energy proton, and this low energy proton, like you see here, can induce a lot of ionizations instead using the Coulomb interaction. Now, in generally speaking, there are two types of energy transfer. One is the elastic scattering, where there is no energy transfer, only change of photon direction. This is important. It's not interesting for radiobiology, that's true, but it's interesting for medical physics because you have a divergence in the beam. Inelastic scattering, instead, is where the photon release energy, can part of the energy if you have a Compton scattering, or the full energy if you have absorption in a photoelectric interaction. Now, these are, of course, the nice movies. This is a coherent scattering. So this is a simple scattering of the photon, the famous Compton effect, where now there is an inelastic scattering with an electron, and then you make an ionization in the electron. The photoelectric effect, where you now absorb the photon and you have an electron emission. The pair production, where you actually, in the vicinity of the nucleus, the photon disappear and produce a pair of beta minus and beta plus, and the photo disintegration. So actually, in this case, the photon at sufficiently high energy can actually induce fragmentation in the nucleus of the target element and produce, for example, photoneutrons. We will see that this effect is very important in radiotherapy. Okay, these things are very well known to the physicists, but let me go quickly through them. Photoelectric effect, as I said, is the absorption of a photon with the emission of the electron. The cross-section as a function of the energy of the photon goes down with energy. All cross-sections go down with energy. Always remember that. In general, we will see that there are exceptions, but in general, they tend to go down because, of course, you reduce the probability of interaction if you run fast. Imagine, I always do the example, imagine that you are in a party, and now if you don't want to meet anybody, you just keep running. In that case, you know, you will have no much interaction. You know, if you have high energy, you will have no much interaction. But if you walk slowly with a drink in your hand, you start to chat, you will have a lot of interaction. You are up here in the curve with a high cross-section and a low energy. However, you see, for the photoelectric effect, this is very far from being a continuous curve. You have a lot of peaks, and this is a quantum effect, of course, because the different peaks correspond to the energies of the different shells in the nucleus, in the atom. Of course, these are atomic electrons. So if you absorb if you are using the right energy, you will completely absorb the photon and will emit an electron. This is okay. This is the angular distribution of the photoelectric effect. You see that it's not symmetrical and depends very much on the energy, especially if it is if you go to high energies, it will be pretty much forward. At high energy will be a forward peak. And most important is the dependence on the atomic number of the target. This is very strong. So it goes with the 4th or 5th power of the atomic number of the target, and that's clear because photoelectric effect becomes much more likely when you have heavy elements because you have many electrons, many shells, so it becomes much more likely to have this kind of effects. The Auger effect is different from the photoelectric effect in this sense. So when you produce a vacancy in the K shell through a photoelectric effect, of course you can have the emission of a photon. You know, you can have a decay of the electron and the emission of a photon, but you can also have a different effect. You can have the decay of the electron with the emission of another electron from the L shell. This is called Auger effect. So when you have low energy photons and low energy electrons also, this effect can be important. You produce new low energy electrons. Of course, this is low energy, you see, because they only correspond to the difference in energy here. You see that this is the energy balance. The kinetic energy now will be the kinetic energy of the first process minus EL minus EL, so it's EK minus 2EL. And okay, and we will come back again to the Auger electrons when we will see the balance of the photoelectric effect and Auger effect, the photon yield as it is called. Compton effect. Compton effect is by far the most important in radiation protection and in radiation therapy because that's we will see the cross-section is in the right range for the energies that we use. It is essentially nothing else than the typical it's a quantum mechanical effect, of course, because you have here the demonstration that photons behave like particles. It's an inelastic scattering of a ball over a ball, but now the first ball is a photon and the second one is a almost free electron. In fact, you see almost free. In fact, you see the residual energy of the photon In principle, you should sum it to the binding energy and to the energy of the electron to have the energy of the incident photon. But in reality, the binding energy is generally small because these are external electrons. Of course, with the great joy of the physicist, I will not give you the Compton effect derivation, you know, because I think it's one of those ansatz that are studied in many courses. You have to do the momentum conservation and the energy conservation on X and Y axis. It's a very nice example, you know, of how works the physics. Just to remember you, of course, the minimum energy transfer, you have it at 0 degrees, where essentially the photon energy is unchanged, and the maximum energy transfer you have for the backscattering of the photon. And in that case, you see, this is the formula for the energy of the electron and the energy of the backscattered photon. The cross section for the Compton effects are given for the so-called Klein-Shina formulas that are expressed here. This is a d sigma on the omega, so it's the cross section per solid angle unit. They are complicated. I'm not going into detail here. You don't need to know. What is interesting is that you see, you can calculate the fraction of the energy transferred to the electron, because this is essentially the ratio, let's say, of this cross section of the cross section for the transmission of the electron and those for the photon. So that's a fraction of the energy transferred to the electron in the process. Now, this is now the fraction of incident energy retained by the photon on the left, and on the right is the fraction of incident energy absorbed by the electron. So you see, when the photon has a very low energy, of course, essentially all the energy is retained by the photon. When you go to very high energy, over 100 MeV, then you can have a large fraction of incident energy absorbed by electron. Where are X-rays and gamma rays that are the most important for radioprotection and radiotherapy? Well, gamma rays are in the order of 1 MeV. They are in this region here, around 1 MeV. X-rays can span from few hundred kilovolts. You see, this is 100 kilovolt, 200 kilovolt. 200 kilovolt is a typical X-ray value, up to 6 MeV, even in principle 20 MeV in some cases when you do radiotherapy with very high energy photon. If you want one number to remember, remember 1/2. So approximately the energy of the electron is approximately in this region here, approximately 1/2 of the energy of the photon in most cases with X-rays and gamma rays. So excluding, if you want, the low energy X-rays and the very high energy X-rays sometimes used for radiotherapy. Angular distribution, here again, I'm not going into detail for the photons, for the electrons. Pair production, as I said, pair production is interesting. This is a case when a photon, in the presence of the nucleus, the presence of the nucleus is very important for the conservation of the momentum. The nucleus must receive recoil momentum. The photon disappears and produces an electron and a positron. This is in the Feynman diagram. For those that are familiar with the Feynman diagram, is the opposite of the annihilation of positron and electrons, where they annihilate and generate two photons. Here is one photon that disappears and generate a positron and an electron. Of course, the energy of the photon there is a threshold here. The threshold is 1.02 MeV, because the resting mass of the electron is 500 keV. So this process is impossible before at energies lower than 1.02 MeV. Now, one important part, we have seen it, the photo disintegration, is when the neutrons are produced by photons. This is also, there is also a threshold for this one. You can imagine if you want to induce the fragmentation, you have to break a nucleus, so you have to overcome the nuclear forces that take together the nucleus. Now, this depends a little bit, depends very much, I would say, on the nucleus that you are considering, and is much easier when you have a large nuclei, when you can essentially scrape the nucleons from the external part, not those that are internal, but they are surrounded by other nucleons. But the threshold is in the order of 6 MeV. The thresholds are in the order of 6 MeV. Now you see, these are pictures showing you the cross-section as a function of the photon energy here. These are in two different materials. The one on the top is in copper, and the one on the bottom is in lead. You see, though, that in both cases, you see the threshold is a little bit higher here, about 10 MeV, a little bit lower here, about 6 MeV. The peak is pretty much the same. I mean, this is about 16 MeV, this is about 13 MeV, and this is actually the spectrum, the neutron spectra that you produce. It is very important for one reason. If you want to do radiotherapy to patients with energies above 6 MeV, considering that in the head of the LINAC accelerator used for radiotherapy, you have heavy elements like tantalum, you can produce a lot of neutrons. And this lot of neutrons can irradiate the patient. It's an unwanted irradiation of the patient. So you irradiate the patients where you don't want to irradiate them. So this is an important aspect. Actually, to be clear, is so important that when, until a few years ago, it was kind of common to have very high energy LINACs for radiotherapy, 25 MeV even. In Frankfurt, there is one at 25 MeV still now. And the reason is that the depth dose distribution is much more favorable, is very much flat as a function of the depth, much more flat than for low energy photons. But it was the generation of secondary neutrons that started to worry the radiation oncologists, to the point that these days, very few machines at energies greater than 6 MeV are actually sold. Then we have the Bremsstrahlung that I didn't mention before, but of course the Bremsstrahlung is the basis for the production of X-rays, this one you know. Essentially, the Bremsstrahlung is the emission of photons from decelerating charged particles. You know, if you are a breaking Brem charged particle, you will produce photons. The energy is shown here. It is the difference between the kinetic energy in the entrance. You always need a nucleus here. You need someone that slows down the particle, and the final energy. And this is now the energy of the Bremsstrahlung. So if you have an accelerator with a maximum voltage, let's say of U, the maximum energy will be EU. This will be the case when you completely annihilate the charged particles and all the energy is converted into a photon. But otherwise, you will have a spectrum. The energy loss by Bremsstrahlung is given by this formula. So you see, this is the energy loss for unit mass thickness. The mass thickness, start to be familiar with it, is the product of the density times the length. It's given by this formula that is apparently a bit complicated, so physicists like simple, and they just write it as E divided by x0. Well, essentially, E is the energy of the of the particles, and x0, this quantity here, which includes all these factors, is the so-called radiation length. Now, the energy loss, if you look at the formula, is proportional to the square of the mass to m to minus 2, 1 over the square of the mass. So it is very, very, very low when you go to heavy particles, and is really significant only for electrons. Generally, not always, but generally, when we talk about Bremsstrahlung, we talk about electrons, and the production of photons is always from electrons. You see that for low energy electrons, the ratio between the energy loss by Bremsstrahlung and the total energy loss, which includes the electromagnetic energy loss, is approximately given by the energy in MeV times the atomic number of the target where you have the Bremsstrahlung divided by 1000. This is important, you know, because it gives you a quick method to see how much Bremsstrahlung you have. For example, for 100 keV electrons on tungsten, which is 74, about 0.74% of the energy lost is converted into X-rays. That's it. So the Bremsstrahlung is not very efficient. It's the best way to produce X-rays. I mean, there's nothing to do. I mean, it's the best way to produce X-rays, but it's very poorly efficient, so you waste a lot of energy. And I give you an example. These days, in radiotherapy, a great trend is the so-called FLASH radiotherapy. FLASH means that you actually give a very high dose in a very short time. We will see that this is a big hype now in radiotherapy because it's convenient and because it seems to have great advantages for the patients. You seem to spare the normal tissue without compromising the killing of the tumor. But you cannot do it with photons. And you cannot do it with photons because of this very low conversion, you see, from in the energy in the Bremsstrahlung is so inefficient that it's very difficult to have an intensity high enough to have enough photons. On the other hand, you can do it with electrons. So if you shoot electrons, then you can reach this very, very high dose rate. You know, we're talking about like giving 60 gray in 1 second, while normally you give 60 gray in 20 minutes, you know, in 30 minutes, even in 1 hour. So it's a you need a very, very high intensity to do FLASH, that because of the poor efficiency of the Bremsstrahlung is very difficult. Okay, now we move to shielding. Shielding is more the topic, the new topic, if you want. It's also for the people that follow with the radiation biophysics. So maybe if you want, because now it's 20 to 7, if you want, maybe we can stop here. Let me stop recording.